So it's been requested to make solutions to the first Desmos activity over discrete time dynamical systems. So let's go ahead and do that. Okay, so we don't really need anything for the intro slide, but okay, grouping together like tiles. Their population of 500 rabbits, so that's already telling me that my initial population is 500. So I can maybe take a initial condition. If there was a 500 tile, let's see, looks like I got a lot of stuff floating around here. Here we go, there's an initial condition. Overlap it. Well, we'll see what happens there. Okay, and is decreasing by 3% each year. So if it decreases by 3%, well, if you want to figure out what that was, turns out this is the updating function for it. So let's go ahead and put this with the updating function. Why do you not, let's see, if I move you here. Nope. Okay, well, nonetheless, that's an updating function for it. And why is this a 3% decrease? Well, how much is missing from 100% or 1? It's 0.03. So if you multiply by 0.97, you would have 3% less than what you started with. Okay, and if I do this over and over again, then my solution function is going to be kind of this form, but not quite. In fact, it's this one over here. So 500 is the initial population, and each year it goes down by, well, it gets rescaled by 0.97. So, and I think I actually lucked out and I put my solution function with that. So this can be added here. All right. Now, tiles like this is just a scrap tile that's trying to trick you. So let's just put this off to the side here. Meanwhile, okay, this would also be something that's trying to trick me. So my updating function has a positive slope. So we can just kind of, I don't know, I group those together just to try and trick me, but really don't even worry about it. They shouldn't be grouped together. Similarly, okay, what is this? This would be something growing from 500. This doesn't really matter. So I'll just plop this over here and out of the way. What's this thing? This would be a population that's also growing. So I'll put this out of the way. It's just stuff I don't care about. Here we go. Finally, I have a plot of an updating function. Okay, I also don't care about this one. Okay, so these are all just things I don't care about. Here's another thing I don't care about. And here's another thing I don't care about. All right. So my updating function, it almost has slope 1. It has slope 0.97. So here's my line with slope 0.97. It's my updating function. My initial condition is the P0 equals 500. And here's my solution function. Now, something that happened when I was walking around and talking with different groups, some people would put this over here, and I asked them why, and they said, well, you can see on the graph, the initial condition is 500 when I plug in 0 at 500. And that's great. You're reading off the correct information from the graph. The only reason why I'm going to keep it in the other grouping is because, well, what do I do with this tile? I could put it over here with the unneeded stuff, but I can actually identify an initial condition. It's right here. And so you might say, well, why don't I just put this tile in here? Well, because the initial condition is not a lot of information. The solution function here is a ton of information. And so yes, the solution function can tell you an initial condition. A solution function tells you things for all points in time. So it'll tell you what happens when time equals 0, but it's sort of its own object in the sense that the solution function is much more powerful. And to try and highlight that, I'm leaving it by itself. So anyway, this is something I would use as a answer worked out thing for this first slide. Let's go to the next one. I initially have 25 plants. Okay, do I see a 25 initial? No, but I see something that's not what I have, which is n0 equals 2. Okay, and I plant an additional 2 vines each month. Okay, so I'm thinking, something like this. All right, so this is a line with slope 1 and y-intercept 2. So I can already see that I'm going to be pairing it with this thing here. So I'll put those two together. So U out of the way. All right, so now if I add 2 over and over and over, repeated addition is multiplication. So my solution function is going to be this tile over here. So let's go put this with solution function. And this exponential can get out of the way. You're not needed. And you're not needed. And You know what? I was going too quickly. Sorry, this is not my solution function. I don't have the initial condition on this tile. Here's my solution function. All right, I wonder why. Sometimes when I hover over, they can attach, and other times not. Doesn't matter. All right, so my solution function, slope 2t, initial value or y-intercept or whatever you want to call it, 25. All right, so let's clean this up a bit. I don't have a curved graph in this case. Get out of here. My updating function, hey, that's this stuff. So I'm gonna put these together. Why can't I? There we go. Great. So I just want to move the whole thing. Move the whole thing. And you can stay there. All right, your extra. Here's an initial condition. So I can put you with an initial condition. Don't care about you. And here's my solution function. Yeah, that looks right. Okay, so I hope this makes sense. Right, when we look back here, when I have to, let's see, here's my updating function. When I multiply by 0.97 over and over and over, repeated multiplication is exponentiation. So when there's a constant multiple for your updating function, that'll become your base for your solution function. When there's constant addition, here we are, for your updating function, that'll become a multiplication of your solution function. All right. Finding a solution function using a table. All right. The discrete time dynamical system has the following function. Here it is. Use the updating function. All right. So I'm supposed to look up here and say, okay, well, 100 minus 3, that's 97. And 97 minus 3 is 94. And 94 minus 3 is 91. And 91 minus 3 is 87. 87 minus 3 is 84. 84 minus 3 is 81. Oh, I messed up because 97 minus 3 is 88. All right, 88, 85, 82, 79. Since it gives me 8, we'll go one more, 76. Okay, so I should have subtracted 3 every time. That's okay. These look like they align a line. And so I am not plotting my updating function. This is a plot of points on my solution function, right? Finding a solution function. How could I know that? Well, for starters, on my table, my input variable is just t, it's just time. My output variable is b sub t. And that's a dead giveaway that this is a solution function. What else? Well, my updating function, here it is. I already know it. I don't need to find it. And what is this function? It's a line. It has a slope of 1, it has a y-intercept of -3, and my input variable, okay, it's not x, but it's just an input variable. It's called b sub t. And my output variable, okay, it's not y, but it's b sub t plus 1. So this is my updating function. I don't need to find it. It's given to me. So anyway, this table I'm filling out is a table for my solution function. All right, based on the points, do you think your solution function is linear or exponential? Well, this looks pretty linear to me. Find the solution function. Okay, so I was subtracting 3 over and over and over, and that tells me that what I have is a multiplication with -3 as a part of it. But then I also have an initial condition, and I started out at 100. So there's my line. There's my solution function. Really, if you go back here to your table of data, you could just start to figure out that, oh, wait a second, it goes, my y value, my output, it changes by -3 as my x value, or t in this case, increases by 1. So you could find the slope, and then the y-intercept is just staring you right in the face in this row, right? So anyway, I know I'm going kind of quick, but hopefully it makes sense. All right, let's do the next one. It'll probably be exponential. Oh, okay, so we have kind of a merging of the two ideas going on. There's like an addition, there's a multiplication. And in this case, the multiplication wins out, and this will look like exponential decay. So, and as far as why that is, well, it's kind of because I have the wrong variables. This is going a little bit beyond where we need to. But if I pull out a 0.5, I can write this as 0.5 times b sub t plus 2. And if I did that, then whatever this b sub t is measuring, we kind of need to do something of a change of variables. So you can imagine it as changing from like Fahrenheit to Celsius or something like that. So if I defined a new variable, so c sub t, and I define it as b sub t plus 2, okay? So whatever the units of the b sub t are, that's what the units of the 2 should be in some sense. Or this is some kind of conversion. I can't make up a meaning for this on the spot. I'm not that creative, I'm sorry. But with this variable, notice if I multiply c sub t by 0.5, my dog just spooked himself. Sorry, he knocked over a crate. Okay, so that would be like multiplying this whole right-hand side by 0.5. And if I did that, I would get b sub t plus 1. And what do I want to say? I was hoping this would just turn out to be the same thing as c sub t plus 1. Do I have any slick way to? Okay, I don't see how to save myself. Maybe I could. Okay, it's not worth it. I was hoping I could do something select and change variables. It doesn't matter. Let's go back to the original plan. So I have my updating function. Let's use it and start to fill in this table. Okay, so I'm going to do something kind of slick because I'm lazy. So I'm going to define a function that does exactly what this updating function does. So 0.5x plus 1, but I don't want to graph. Like, this is not what I'm interested in. But now I can use it. So f of 100 would tell me the next value I'm supposed to do. And in fact, I already know what this is. This one I can do in my head. It's 51 because, so B0 is 100. If I plug in 100 for this number here, then I get 50 plus 1, I'll get 51. But on the other hand, I was plugging in B0, so the output should be B1. So anyway, 51. Now when I plug in 51, I have to do half of that. So that's 25.5, and I add 1, I'll get 26.5. And then I have to do half of that, which is 13.25, and I add 1, I get 14.25. Half of that is 7.125, and I want to get 8.125. And if you don't want to have to do that, then you can just reference f and enter the previous value, and it'll compute it for you. But then maybe I want to, right, it'd be nice if Desmos told me what this is. So another option is I have Desmos tell me. So after I've done this, I can just ask Desmos, hey, what happens when I do this? Okay, so 5.0625. That's telling me, okay, so b sub 4 was my 8.125. If I plug in b sub 4 to this function, that's what this is doing. And the output is 5.0625. So, okay, 5.0625. And let's go ahead and plug that in. 5.06625. 3.53125. 3.53125, and honestly, this is good enough. Okay, so this is good enough based on the points in your table. Do you think it's a linear exponential? And this looks exponential. Okay. Do you think there's a horizontal asymptote? Okay, so let's start to move this. And all right, so then now I do need to continue in order to see if that's the case. And there will be a horizontal asymptote. And I believe that horizontal asymptote is actually 2. I think it's what you get when I did that factoring thing before, where I wrote this as, I factored out the, sorry, I had 2 on my brain. I factored out the 0.5, and I wrote this as b sub t plus 2. Let's see, can I solve in the, well, I guess we can just look, if I plug in 2, then half of 2 is 1, 1 plus 1 is 2, and so you see that what I plug in is what I get out. Okay, so this doesn't matter. Anyway, if I continue, if I did f of this number here, okay, then I'm going to be real lazy and it's going to look really weird, but I promise I'm doing the right thing. that. Now I want f of, which is this. Okay, so I've got a lot of points here going on. Let me also just go ahead and plot. I don't want a notes. I want something like y equals 2. So you can start to see that we're pretty much going toward that horizontal asymptote. And you might say, well, how do I know we don't go towards 0? Well, if you crunch these numbers and do yourself, you'll see that we should get closer and closer to 2. But you can also, now that we know more, we've gone further in the class, you can solve for the equilibrium by setting, you basically just want the equation b equals 0.5 b plus 1. Okay, and then you just solve for b, you're going to get 2. So anyway, where are we? Aha. So yes, it looks like I'm approaching an asymptote. And so how do you find a solution function in this case? So this is beyond what we would ask of you all, but how do you do it? Okay, so the quick and dirty answer is when there's a multiplication in your updating function, this will dominate because this means there's exponential decay or exponential growth, and it dominates. That's very hand wavy, but okay. And we, for a moment, want to pretend, whoops, that this is the only updating function that we have. In which case, we know the solution function has the form like 0.5 to the t. Okay. Anyway, that's not what matters. I'm gonna just ruin Desmos because I just killed all that stuff. It doesn't matter. Okay, but what's our real updating function? It's really this. So if we go over here, if I just plot something like 0.5 to the t, all right, well, we can barely see something just popped up. Let me get rid of this right. Normally, we also have an initial condition. So I should do 100 times 0.5 to the t. And now you can see I go through the correct initial points, but my horizontal asymptote for this function is 0. I'm creeping down below the red dots. And I could make the horizontal asymptote 2 by just adding 2, but now I have the wrong initial condition. It turns out what you want to do is not use 100. You want to imagine this is some number c, okay? And before I had c is 100, okay, and we were a little bit off. You can't quite see it there, but now you can see it. This gray dot doesn't match up with the red dot. If you plug in t equals 0, then 0.5 to the 0 is 1. So c times 1 is just c. And so I have c plus 2. C plus 2 is what I get when I plug in 0. Maybe I should type that out. I have c times 0.5 to the 0 plus 2. And so the reason this is saying 102 is because c equals 100. So this is saying 100 times 1 plus 2. All right, but what I'm supposed to get when I plug in 0 is 100. I'm supposed to get that because that's my initial condition. So then you just ask yourself, what should c be? And the answer is c should be 98. That's how I get 100. And now my gray dot covers my red dot because this is the curve I want, and all my red dots lie in the correct curve. So the solution function, it turns out, so I could write this down as like plus equilibrium. All right. So this 0.5 to the t, that's hinted at by the fact that I have this constant multiple in my updating function. And then how do I know to do a shift up by 2? In general, it's shift up by equilibrium. So in this case, my equilibrium is 2. That's the number I plug in, and it'll be the same as I get out. And then I have to find c by using the initial condition. Okay, again, that's beyond the scope of this. So there you go. That would be a very hard question, by the way. All right, analyzing. So I believe maybe we can drag this. Yes, we can. Great. All right, the function in blue is the updating function. Slider low allows you to change the initial condition. Here, let's go ahead and play. All right, and there's some lag, so let's go ahead and slow this down a bit. And okay, so we can move past the equilibrium that way. Great. Cool. If the initial condition is 0.5, describe the behavior of the solution function. Okay. So if my initial condition is 0.5, okay. Describe the behavior of the solution function. Well, so I begin at 0.5, and one time unit later, I am at whatever this y value is, which in this case is 0.75. The next time unit, I'm at whatever this y value is, which is 0.9. The next time unit, I'm at whatever this y value is, which is 0.9654. And as time goes on and on and on, I just check the y values of each time my cobweb hits my updating function. And if I zoom in a lot on this point, you would see that this cobweb gets really bunched up. And I'm just getting closer and closer to this equilibrium point here, which is 1. So describe the behavior of the solution function. My solution function increases. It increases slower and slower and slower. So it's kind of like a, think of like a square root. Like I increase, but slower and slower and slower. Okay. And I'm approaching an equilibrium of 1. So in fact, unlike a square root, I'm going to have a horizontal asymptote. So I have to increase and get closer and closer to this line, but I can never cross it. So my increasing kind of slows down and melt off. And if you think, well, how can you always increase but never cross something? I forget which old dead philosopher it was, but imagine I'm 1 meter away from a carrot, and I really want that carrot. And every second, I step half the distance between me and that carrot. So I start out 1 meter away. 1 second goes by, and I step half a meter, because that's half the distance. Another second goes by, and I step a quarter. Another second goes by, and I step an eighth. Another second goes by, and I step a 16th. And then a 32nd. And then a 64th. Anyway, I can always continue to advance and never quite get where I want to go. So it's possible to always increase and never quite get there. Anyway, that's what's happening. My solution function is increasing towards 1, but it doesn't quite touch it. All right, identify the x value of the equilibrium point. Okay, sure. So that was 1. The points below. If they're correct, you will see the points below the graph. What is this asking? So identify the x values of the equilibrium points. Okay, so there's 2 equilibrium points. One of them is 0 down here, and the other one is 1. Okay. Let's see what happens if I guess wrong. So maybe I'm guessing 0.1, and it's not there. Okay. So great. If you guess correct, there it is. What happens if I put in the other order? I make U1 and U0. It's okay too. So good. Identify each equilibrium point as stable or unstable. So we need to move this slider all the way down here. And the fact that there's no cobweb approaching this point already tells me that I'm not going to approach it from the left. And we actually already knew we weren't going to approach it from the right because we began in this region over here, which was to the right of that equilibrium point. So this is 0 is unstable and 1 is stable. All right, second to last tile, new updating function. Same function, the slider below. Yep, sure. If the initial condition is 0.5, describe the behavior. All right, well, let's see. So the first, all right, so x0 is 0.5, x1 is 0.2485. I'm reading the y value of when I first touch my updating function. And then as I continue to read y values, I'll get the next number in the list. So x2 is 0.101, so on, so on, so on. Okay. So what's happening to these y values? Well, they're decreasing and they're heading towards 0. Good enough. Identify points of equilibrium. Well, again, there's 0, and again, there's 1. Oh, can't hit enter. Click it. So they're highlighted. Yep, that's fine. Stable or unstable. So I'm heading towards 0. It looks like 0 is going to be stable. Technically, I have to check it on the left as well. And you can see I head towards it again. So 0 is stable. And I've already checked 1 on the left, and we can see that no matter how close I get to 1, I just head right to 0. If I cross 1, I head away from it. So 1 is unstable. And on both sides, I head away from it. All right, last tile, stable versus unstable equilibrium. Think about the previous 2 cobweb exercises. Can you make any observations connecting the relationship between the updating function and the diagonal line to whether an equilibrium is stable or unstable? Let's see. So here, my stable point is this one, and my unstable is here. Here, my stable point is this one, and my unstable is here. So it would be interesting to see all the different things that you all came up with. I know the answer ahead of time. The answer has to do with the slope of the intersection point. So if when I intersect, my slope is bigger than 1, which this one's just a little bit bigger than 1, then I'm going to be unstable. I'm going to head away from it. And if my slope is less than 1, and I mean an absolute value, so I got to be between -1 and 1, which this one is, right? This is a pretty shallow slope, and this point will be stable. Similarly here, the shallow slope is down here at 0, it's stable, and the steeper slope is up here at 1, it's unstable. Okay, so that's something I could put in here. Stable if the slope is shallow, right? We're just trying to do some observations. Okay, there you go. I hope you enjoyed the video. How do I